So first of all, I will thank Cihan for inviting me to this seminar. And as you can see, my presentation is on computation and quantum contextuality. There's a reason I chose this title for this presentation. I could have chosen more particular work that I'm doing, but there are two reasons. There are two reasons for choosing this title. The first reason is that quantum contextuality is being investigated and researched from different communities, and I wanted to emphasize that the main point that we are interested in, or the goal of our work, is to seek computational understanding of this contextuality. And the second reason is that I'm not going into details of the formalism, but rather give you an overview, and maybe for the next talk I can go into the, if possible, I can go into the internal dynamics of my work. So giving you a short academic background, how it came to existence, how we worked on this facet. Actually, during my doctoral studies, my supervisor, Mario Rossetti and Emanuela Marilli, they had proposed a theory. They call it as topological field theory of data, and it's an ambitious theory and still ongoing. And the theory is about a general framework for complex systems, evolving complex systems like real time, like brain, epidemics. There are so many complex systems nowadays, and there are so many layers of this theory. And one of the layer is the computational layer. So they want to understand some frameworks that could go beyond Turing, possibly. So this is the main crux of this theory. And if I would have to define in a very simplistic way what this theory is about, it's to extract and mine the hidden patterns in the data that's output from the complex systems, and to provide them a potential semantics so that they could be expressed. So it's a very naive and a very basic, so that everyone can understand what this theory is. When I got. And on the other hand, there was during my doctoral studies, there is, you all know Samson Abramsky and Rui Barbosa. Samson Abramsky and Adam Brandenburger, he's not in this picture. They were working on mathematical generalization of quantum contextuality. And in particular, he was working in quantum sheaf theoretic interpretation of quantum contextuality. And along with his postdoc researcher Rui Barbosa, they developed several aspects of this mathematicalization of this quantum contextuality. And they were invited to our university, and during their course of interaction, they were very sure that there could be some correspondence between their framework and also the framework of Abramsky. So what is the main question that we are interested in? It's to say, what could be the model of computation that could express this quantum contextuality, or we say it in terms of as a mathematical, we say it contextual semantics, a new kind of semantics. Because Abramsky already applied this semantics to relational databases, constraint satisfaction problems, logic everywhere. So we wanted to test it in computation. So this was actually my functor in the PhD. So this was going from the subspace of these to this to see, and we got some insights. I don't know. But
maybe we can try just disconnecting this part. Maybe that's the reason. I don't know. Well,
okay. Yeah, now it's. So I think. Okay. Now coming to the topic, you know more than me, I suppose, what quantum contextuality is. So non-locality and contextuality are the fundamental features of non-classical feature of quantum physics, and they have role everywhere in quantum speed-ups, quantum advantage, and they surpass classical computing in terms of computational power. And as you already know, that contextuality is actually the impossibility to assign values to the variables of a system simultaneously, because the property that you are measuring simultaneously with what other person is measuring in the same instant of time, it makes things contextual, and there is some inconsistencies in the system. And there have been, due to the primary role played by contextuality, there had been several mathematical generalizations. For example, this feature was um, was was understood or viewed from the concept of sheaf theory, graph theory, hypergraphs, algebraic topology, probability, and we are interested in one of the. Yeah, it goes like it gets a spark. Maybe I have some charge.
I don't know, because
I
this
think I have
is the
some.
electricity and this is connected to the HDMI.
So maybe I have accumulated a lot of.
Oh, maybe you're overtime. Okay. But yeah, maybe at some point we need to plug this back in if the battery life
Okay.
left, but this is also giving some issues here. Yeah, I can move it down. Yeah, hide this, hide the panel. No. Oh, I can move this.
Maybe.
So let me try. So is it because of you or?
Let me see. I just try.
I think, yeah,
I
think it's maybe coming from
you. So one of the interpretation is through sheaf theory by Abramsky, and we are interested in that only. And what it says that this contextuality arises due to cohomological or topological obstructions that make something that make things locally consistent, but globally they are inconsistent. And the setting part is just a simple setup. So what we have two agents, Alice and Bob, as you all might be knowing it. Just to recap, and Alice has a 2-bit register, 1-bit register, like two registers of each of 1 bit, and Bob has the same. So what Alice can do, Alice can select one of the register, and it can see what is the value inside the register. It can either choose A and or A dash, and similarly for the B, for the Bob. And when the Alice chooses one specific register and observes a value, either 1 or 0 here, so either 1 or 0, depending upon how we are formalizing it. So it's so for example, Alice chose register A, and when it saw, and just assume that there is some source from which these values are coming, and the source sent 0 to A, and when it observed, it saw 0, and this is the event of the system. And you can do similar events. You can record all the frequencies of these events.
Okay. Yeah, if you find that out, the computer here, maybe I can just.
Okay.
Yeah, that's safer.
I don't know why.
Yeah, I think that's. Let's see if that happens.
I'm sorry for this.
Okay, let's see. Yeah, that's good.
Okay, so I forgot to tell you that they might have communicated before the experiment, but once they are apart, they are not allowed to communicate. And similarly, these events can be iterated several times, and you can get the frequency, the frequency table like this. Okay, you can get, so when this experiment is done, so it's a basic setup in the left side, and on the right side there is probability distribution of the events. For example, this one is for a specific model which is called Hardy model, and you can see that when Alice chose A and Bob chose B, and they observe, for example, 0, and Bob also observes 0, and you have a probability P1. In the same way, you can just read this whole table. It's Hardy model.
So you model itself like the scenarios.
Yeah. So, see, the scenarios. Possibilistic, yeah. Like Hardy. And we can also do, we can also make it more general, like we can ignore probabilities and just focus on whether event is possible or not. For example, you have this table that we saw in the earlier slide, and what you do, you just say if probability is greater than 0, then you assign 1 to it. And if there is no probability, then there is 0. And we get this kind of table, the possibilistic table for Hardy model. And you can also, you can play with it in a geometric way. For example, contexts can generally form a simplicial complex, but here it's a square base because we are in a specific scenario. So you can see these contexts are connected to each other, meaning, for example, when A is observing what and B is the other context, and when you can. And you can then put outputs as fibers or stalks in the sheaf theoretic sense, and each stalk has 2 values, 0 and 1, as you can see here. So it's easy. So it's like saying the same thing but in a geometric way. Like Alice chose A and Bob chose B, and they observed 0 or 1 or 0 or 1, whatever you can see. Now, possible event means path between the stalks. For example, if you see this is all possible, so you can see when when AB is 0 0 0 1 1 0 and 1 1, all of these are possible. So there is a path in the fiber space like this. And similarly, you can do for the another path, for example, like this, and you can do for other path and another path like this. And for example, this is not possible, so you will see there is no edge between the output space, the fiber space. And of course, there you can also do some linear combinations, maybe another like this. You can take this and you can see how the path moves in this space, and also maybe. But there is one context AB at 0 0. If you try to go around it to come back, you will not be able to come back, because if whatever possibility you chose, you cannot come back to the same position. And implicitly it means when you are able to come around this fiber space, it means the ambient topological space, if it's a simplicial complex, for example, it's collapsible, it's acyclic. So that's why you are able to measure all the contexts simultaneously. And this acyclicity is actually the essence of quantum contextuality, that when you say not all, when you can simultaneously measure all the variables of system, that means it's collapsible. And that's why you are able to form the in the fiber space. And so this is a particular context in the Hardy case. And there is also a logical way to define it, but I won't go there. So that's the experiment. So now what they did sheafification of this quantum contextuality, because it's only on the sheaf. Okay, so it has if you don't know sheaf theory, you just have to remember this. What sheaf theory is? Sheaf theory is just you have 2 components. One is this component, horizontal component, and the other is vertical component. In the horizontal component is of like topological type, mostly it's a topological type, and this is algebraic type. So it can be simplicial complex, and over the simplicial complex there could be sets or anything. So I have an example to get to make you understand what sheaf theory is with a very basic example. Because I was conveyed that there are master students also, and by Aziz. So for example, thank you. I did not want to write, but I saw the videos, everyone was writing, so I thought something should be written on the book. Is it? Okay, yeah. I will draw it. So we have, first of all, we have a simplicial complex. Like, are you able to see it? Okay. Yes. So this is like this. This is bracket. So just see if there is edge, like V1 is connected to V1, V3 like this. So it's like now I will draw also V3.
That hardware is filled, right?
It's filled. It's filled. I hope I draw it correctly. So it's like all the relations, like if you open it, it's like this. And this is the horizontal component of this sheet. And what vertical component does, you're just putting any, for example, vector space on it. Like if you can, and here you can put any dimensional vector space to any of the this is. To say that now you have this horizontal component and you are putting some data on each of the vertex. And this putting of data is really very interesting. You can see it in a lot of places. For example, in computation, there is a model of computation called bigraphs, which is very novel in 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 what's called in corresponding to the real-time problems, or in gauge theory. There is also this putting of data on the vertices. It's almost very interesting. It makes interesting. Yeah, yeah. So you no, it's going from so little to bigger. These are dimensions. Just randomly to show that in fiber bundles you cannot do that. You can have. Yeah, but I did not put that, but it's just to give them a glimpse of what this is. So you put the data on it on each of the simplex, and then if you can then put real, for example, here. You can check it in the meanwhile. So based on this dimensional interval space, I put some random, values. And if you do some computation, the whole of the square, commutes. You can go everywhere. Like you can. So in this sense, this is if you're going from here and here, it's a local section. But if you're able to commute all the diagram and go anywhere of the sheaf. So this is a base. Just to give you an intuition of this is a base space, a slice of a base space, and if I change a value, for example, if I change a value here, I just change it, for example, 20, and here I can choose 2. Then this is not you will not have this here it's 10. I forgot. So here you cannot 1. So here you cannot commute the diagram because you cannot have these don't multiply to get local section, but you cannot have global section. Notice that like it's filled, but still there is non-existence of global section. So the non-existence of global section depends upon first the non-triviality of space. If there is non-triviality in the space, for example, there's a hole or something like that, and also it depends upon the values, how the fiber or stalks are twisted into each other, like what are the values of the stalks, and they can also produce some. Huh? Basically, yeah. Maybe I is do you there's no cycle.
No, right?
Huh?
So you said there's a global section, but there's always a global section.
Yeah. There's always, and the values that I put first before I changed it was all consistent. You can go from one place to other, but as you change the value, everything changes. So this is what I was saying. Phenomena of the phenomenon of non-locality contextual is characterized precisely as obstructions. These obstructions or non-trivial obstructions in the space, maybe. So it's this is what I was saying. There's acyclicity means collapsibility means non-contextuality, because all of the variables are collapsible, means we can simultaneously assign value to all of them, and they are or you can say they have vanishing cohomology if you are doing this kind of procedure on the space. And this is because I did not describe the sheaf theory. This is if someone wants, he can see that how this sheaf theory corresponds, how sheaf theoretical concepts are correspondent to the quantum contextuality. For example, you can see a topological space with measurement cover M like this. Maximal measurable context, and it corresponds to the in quantum contextuality. It corresponds to the set. EU is a set of all assignments of outcomes that you can get. Local section is just an assignment for a single outcome, and these are restriction map that they were saying that it should go from larger to smaller, and how you move like this, EV and EU, like these. And the global section means when all the outcomes work together, like they are consistently, you can move around. And empirical model is then is defined as this. Whole of this is empirical model, and this is what we are talking about. I think it's clear.
And the other side also exists topological space is in order.
Mm-hmm.
The left side is the same, right? The topological space.
Which
in the right side.
In the right side, what?
Yeah, it's still topological space.
Yeah. So.
Yeah. It's just a section, right? Yeah, but if there is a generalization. Yeah, just that,
yeah, it's a set. It's a set. You give discrete topology to it.
Okay, yeah, this is generalization, but here it's because we take this union like C and then what you cover. So
it's an open cover. Okay. So C is the open cover over this, which open this space.
Yeah, from say for like the security.
Yeah, yeah.
As you say.
Yeah.
Yeah.
So now the question was put by Abramsky and his students is actually in the thesis of Giovanni Caro, that also in the paper, that is there a gauge theoretic fiber bundle perspective on contextuality that generalizes the sheaf theoretic approach. So this was the question. This is one of the questions that we will slowly approach, and this is a fiber bundle. Uh, does everyone know about the fiber bundle? No. I can give you a basic. I just prepared some fiber bundle. You want me to put? So I won't give. I won't get into the definitions because it's if I say definitions, it's same for the people who don't know. But it's a there's a very canonical example of fiber bundle which is of cylinder. So we have a cylinder, and this cylinder could be infinite from both sides, and then and we have this. We specify a particular circle over the cylinder, which we call S1. And we assume that the height at S1 is 0. So it means the height above will be positive, for example, and down will be negative. And if we select a point in this on the surface of the cylinder, it's a hollow cylinder, and we can express this in a coordinate system. For example, we can say this P has how we can see how much where is this project on this circle, and which is for example A, and what is the height of this, for example B. So with S in place, then you can so every point on the cylinder can be given coordinates, and similarly for example another point Q, you can do the same. For example, it's C, and this is D, for example, and it's C, D. So you can create this ordered pair all over the surface of the cylinder, and by this you can divide the space into 3 spaces. One is the total space, which is the cylinder, and S1 is the base space, and R is the fiber space. So and E can be in this case, E can be shown as a product, Cartesian product of, like you can see like this, Cartesian product of a circle with the fiber like R, which is like AB, such that A belongs to S1 and B belongs to R. And then you have a pi projection. In here it's easy, but generally projection pi is from the total space to the base space. It's called projection map. Like it's very easy to see, but sometimes spaces are complex, so you have to project. You have to have a projection to, which means like if pi of AB, it will give us A, because it's from E. Because in here it has 2 coordinates, but when you project, it becomes 1 coordinate. It just is A. Okay. In the same way, pi inverse of A will be diffeomorphic to a real line. Now the real line, or the real line here is RA and here RB. They are different, but they should be diffeomorphic to the RC this C. So they are diffeomorphic to the generic real line. So there are 2 ways of looking at fibers. One is between the fibers, but they all should be diffeomorphic to some standard fiber. So I will just explain this diagram. I think it should be here only. So it's a, so keep this in mind. So it's a total space, and this is the base space, and this is a topological space X, and you have a cover over the topological space like this. For example, you have a point P through this projection map, pi inverse P. There is a, it's an open set here, and it should be open set here also because of the definition of Weber bundle. And if it's P, there is a section in here which corresponds, which will be it's one to many, because you can see here there are many values of this real line, but for one parameter there are several values of the real line. So in the same way, for this P, there would be many values, and in the same way for this and this, and you can use these projection maps. And then they are also now this pre-image of this UI is also should also be diffeomorphic or to a standard fiber F in the same way this. And also there is a condition called local consistency, local trivialization condition, which means that if you take some open set here and put it here, then it should be, any point would be described as a Cartesian product, like there, like I showed you here. So it should be a Cartesian product of UI, that's here, which and then fiber, which is this, because it's because it should be diffeomorphic to the standard fiber. And through pi and psi means pi takes it like this, and then psi actually this is actually this. So it's like together like this. You can see it's segment from this and segment from this. It's called local trivialization condition. And similarly for another, you can do the same by different trivialization maps. So these are called bundle maps, and this is called projection maps, and these are called transition functions. So this is always possible, locally constant. This is always possible that you can always have a section, local section. You can go, but this is a problem. Like this is not always possible between different trivializations, like UI cross F and UJ cross F. There, it's not always possible that there will be that they will be consistent. That if you see this in this term, that means this. If you call, if you say, that means one at this intersection, the trivialization map through one trivialization would fall in one space, and the same point at the intersection would fall in another space. So it's not important that they would be consistent. And so this is like a way to say how things are changing in the bundle theoretic perspective and sheaf theoretic. So, for example, these restriction maps are going to be now transition functions, which what is there? So gluing. So you can see that I think it's. There is a that goes from here. What? You have like operations that you apply on sheaf theoretic functor that give you bundle or something. No. Maybe there is like. Yeah, there's a canonical way of going from bundles to sheaf theory, and of course, and also you can go from sheaf theory to bundles by ETL construction. Yes. By what? ETL construction. I don't know how to pronounce ETL construction. Yeah. So you can go from there. So, but it's not. But there are some restrictions to it. But you can go it. So it's like you are now, for example, just not looking at this, just saying, it means like the restriction maps now are these transition that I showed you, transition maps that will decide the global and local consistency. And similarly, yeah, here I said ETL space, like it's like this. And this is actually, sheaf theory is more like a functorial way of visualizing this, and bundle theoretic is like a geometric or topological way of visualizing the same. So if you think about like a refined member like F, the fiber of one line. Yeah, it's an outcome space. So it's the same. The only difference is that here you can have here you induce topology to it. Here it's like a function, you go from function to function. Here there are more conditions on going around. So, and now this is very complex. I cannot go to this because we did not stop at a bundle. It was just an introduction. But what we propose is an evolving simplicial bundle. It's now a bundle that in which base space is changing and fiber space could also change, and the collaborative interaction between the both. And the motivation comes from a theoretical computer science perspective, because in theoretical computer science we are, for example, if we have a Bell experiment and he's doing an experiment, he does not know a priori what could be for example, he's doing an experiment, for example, checking the polarization of light or something, getting some data. And this data goes into for example, a machine, and it's doing some topological data analysis. And it's making some space, for example, one whole space, or it's evolving. No, but me as an experimental does not a priori know what would be the topological space that would be associated with my data. I will not know a priori. So this is the conceptual underpinnings of why evolving simplicial bundle is there, because when we have an empirical model and we try that we see stepwise iterative way in a computational way how this structure is evolving, and where does it finish, like what could be the topological base space associated with this empirical model. And it would not be abruptly in one go, but it will evolve iteratively. That's what evolving means. So I think I should not touch this because it's too much. Like if you want to, I can, but it will not be understandable. Maybe if you want, we can do another session for this one especially. But now this is. Can you go back? No, this. So so we have what we are given. We are given a Hardy model, like the table that I draw. Do you remember that table that I draw? So this is the first. So a conceivable step to construct a base space. So first of all, this is not only the approximation of the base space that we try to extract from the Hardy model based on the tabular data that we have. So how we will do it combinatorially, like how will we do? So first step would be the first step that we do is to make a kind of a power set of all the possibilities that the experiment can happen. For example, in one go, Alice can choose A dash, Bob can choose B, and then Alice can choose A. But it is also possible that Bob will first choose and then Alice will choose, and so it gives a kind of discrete way of looking at this experiment overall. So
we identify the same label. We identify the same label twice.
Yeah, it is identified, but yeah, it's identified, but it's like in different time frames. Like you can go like this. So overall, both of the Alice and Bob have the choices like this. No, it's the base. We're constructing the base. Yeah, no, it's not full. It's like we're starting. Yeah, like you have Hardy model. There is a table that is associated with the Hardy model. Same table, yeah. And now, because it's impossible to extract a space from the table, it's more inspired from the higher dimensional contextuality, where interaction is much more. But in this table, it's very specified. So what we do? We first try to analyze this table in terms of like what are the possible what if it has four, for example, A dash B dash. So its power set would have a discrete topology. Like this is the basic way to view how many whatever two Alice and Bob can do. Like it can go from this, and from this. Did you understand?
No. But let's see.
So I'm saying, for example, this space gives is a combinatorial realization of the table, like of the measurements that could happen.
But the measurement space is just square, not square.
Yeah, of course. Yeah, it's when you say a dash b dash, it's a boundary of a square. But this is like we are trying, what we are trying to say, that we can show this by a bond by a square, but we are trying to extract a combinatorial structure like a base space. So this space says that when you say a b a, when you measure a dash b, when a dash b dash, this is a square, and then there is a possibility in the same time that it's a snapshot that which no, not now. Yeah.
Is it the square still or the triangle still?
No. It's just a representation of from a table all possibilities that this table can do. Yeah. These are measurement labels. Yeah. Now here now this gives more, you can say, redundant or more information, in the sense that you can have these contexts interacting, or these contexts interacting, or these contexts interacting. Yeah, right now there is nothing, because we're now yeah. And
this is currently done. Currently done.
Yeah.
They have the edges multiple times, like 80 repeating a couple of times.
So yeah, the point is it's a
So what does the diagonal plan do?
these are just these represent nothing. These are just if you cancel them, there is no impact on the topology of the space. It's to say that this gives more maybe I'm confusing, for example. And this is also so we have this space. So we have this set. Yeah, B and A and B prime. Like, yeah, A dash B dash. Okay. Right. So what this space is it is of course it's like you were saying, like this A B A.
Yeah.
But what this space is, it is to say, because our goal is to have some combinatorial structure that will act as a base space. So we want to see, so what this space does, it gives you all the possibilities in which the measurement can be performed. For example, this one. So for example, Alice can choose A, then Bob can choose B. After some time, Alice can choose A dash and Bob can choose B. But it's not only way it can do. Maybe Bob will choose first.
But why can't you just go for measurements? Why do you stop there?
Because there are only four permutations. Like permutation is between the four.
Oh, okay.
So it's a kind of a permutation, not permutation, but it's a different ways the experiment could be performed. Do you understand my point? So it's like when you do this, you are just on one line, like you are saying, okay, this is a square, but you are giving opportunity, because you have to deal with now a space. So you are saying, okay, in this space it can have any possibilities, like maybe Alice will choose A like first, then this, or maybe somehow at some time or in the same time this can choose like this, or this can choose like this. Like these are different. Yeah, like Bob chooses first like this, and then Alice chooses. It's like a kind of all the possibilities that that these four elements can exhibit, like all the possibilities. What one? Yeah. Yeah, these will be paths after some. Yeah, it's because it's like this only. I can I have only 4 contexts that I can. Yeah, yeah, yeah. So now maybe I do more, I say more maybe. For example, now this is trivial space. It gives you nothing. Now the point is, let us suppose I have to see the table, and there are in the table there is, for example, a dash b is at for example 0 0 is a non-possibilistic event. If I physically choose, if I physically draw it red, it's obsolete. Like because in this space we will use discrete Morse theory to for example, if I have to represent a context, for example, a b dash is red. For example, red in a sense critical, like it's not possible. If I physically do it, like if I choose it and do it, it's obsolete, because I'm not giving any rule that can change this, that can change any of the simplices to to red. And also at the same time, the space, when I will use some theory like discrete Morse theory on it, the space will also constrain how to put these labels, how to. So there becomes 2 problems. One is context indistinguishability issue, and other is the element of choice. For example, if I deliberately put anything, for example, I see it's an absolute argument, but just to say, to make you understand, if I choose if I say a dash b at 0 0 is 0, if I choose physically and change it into red, it divides the agents of the element of choice. So you are pushing it, like they are not doing it of its own. You are just pushing that this is not possible. And second, if you change one of the instance into red, there are many, like there are 5 more. So which to choose? So this is a problem. Like how would we decide? For example, if you choose a b dash as red, then there are other a b dash, a like a b dash, a b dash. So you cannot. You should have a rule, or you should have a kind of function that can decide, that can make things critical, or based on the table, or generic. So that's why what we do, and there are many reasons. So we are just extending it to we are just identifying the boundaries. Yeah, yeah. Maybe I should.
Excuse me. Excuse me, may I ask? I still don't understand, like, where is the topological space? It's like looks like a torus for a bit, but yeah, I don't understand where is the topological space.
Yeah, it's a torus, because if you compute the Euler characteristics like vertices and edge. Yeah, but yeah, it's a torus, because when you identify these like this, and it will be like this and like this, it becomes a torus. Yeah, I was just trying to put everything from the scratch, like. Yeah. Then we define we put a discrete Morse function on it, like assigning each. What is discrete Morse theory function? It's like you are assigning numbers to each of the simplices in in an ascending order, so that as you go higher, you put higher values to the higher simplices, and when you do that, you are not. But there becomes a problem where you cannot assign values in this rule, under this rule. So sometimes, so what you have to do, you have to turn some of the simplices as critical. Like when you go from this has no value, so because of the imposition from the discrete Morse function, so you turn these red.
Oh yeah, currently we don't know about
No.
we will learn about
These are the rule is to, as you go. No. You just say, okay, if you have a edge, you have lower number, and when you can put any number. Yeah, but it depends upon how you are coming. How you come up in this, how you walk through this space. But it does not depend on that. But you start yeah, it's a yeah.
Is it like
which simplistic condition? Yeah, yeah. It's yeah. So it's like numbers are not important. You can choose any number, like but you have a order. When you go through, you have to provide less simplicities to less number to lesser simplicities, and as you go, you get stuck somewhere, and the stucking you don't have to number it, so you put it red. So in this case, this is the final, final, not final. This is the another step, like we did discrete mostly. Now here we cannot now there is a now you cannot put all the non-possibilistic events in one go. So it's kind of iteration. So you're in the next step. So here A, B dash, and these got red depending on the table. But there is more. There are more events that are non-possibilistic. So we have to also put them. So what we do, we attach another space so that we iterate it like this. We attach another torus to it so that it can get this. It can also include more critical simplicity, more non-possibilistic events from the table. So if you see, so like this, this could have been more. If this is the background theory is this evolving simplicial bundle, but here we are dealing with example. That's why it gets I skipped some things. So now you have this and you attach this with this. So there are more simplicities. But now the simplicities will be, there are the simplicities will be valid or invalid. It will depend on, first it will depend on the table, and second it will depend on the fiber space, which is the next step of our which is the next step. It will depend upon the fiber permutations. So the fiber permutations that are not included in the context, that are not included in the fiber space, they will not be those will be nullified. For example, this or this, or if this and then we do the third iteration where all of the behavior gets all class of behavior from the table gets expressed. For example, if you can if you can do like in this, you get all the expressiveness of the table. You get all the simplicities that are critical, but not all the critical simplicities would be validated. Only those simplicities will be validated that will be considered the table, or that will be considered by the fiber space that will come after this. But notice, because there are equidistant critical points, there is possibility that there is a possibility that loops can form in this space. Now there is a huge theory behind this, like you can have loops. You cannot have loops in discrete mode theory, but there are equivalent discrete mode theory, and it's discussed in the paper. But for now, you can just remember that there, due to these equidistant simplicities, because it has to. It's like this is like a gradient flow here. Everyone going here, but here it gets confused in some way, like from where to go. It's like a defect. So the loops get formed, and this is interface loops. We call this as virtual loops, and these are the critical simplicities. So in this space, there what we did, we iteratively put all the non-possibilistic events in the table, and the AA where it shows contextual behavior, it arises from these loop things. So what in our case, we define strong contextual, strong collapsibility as a measure of this as a measure of contextuality. If a simplicial complex is strongly collapsible, which means that it has no critical simplicities and it has no virtual loops, then it's non-contextual. But if it has any one of them, then that means that it's contextual. And that's why an observer here will see from the fiber, it will see everything it's not red, it's like possible, it's not critical, it's possible, but it does not know that actually globally the space is, he's in the another space. So locally it's consistent for the observer, but globally he's somewhere else in the new space. So of course there are few points to make here. This space is maximal space. I have already worked on it. I have refined it in 2 torus. So it's a it's a surface with three holes, and you can refine it into two. The reason why couldn't I do in a priori, because I had to follow some pattern and then I can do the reduction things on it. So, but we are only giving the maximal space. And secondly, due to the usage of discrete modes theory, there is also redundancy. There is also some redundancy due to the use. For example, we are trying to we did the same with the Conley theory, or we are trying now with Hodge theory, so that things get more tighter. You know, we don't have to go like this, putting all the more redundancy in this. So this would be the base space for the Hardy model, and this is the fiber space. Now, for the fiber space, we know we cannot take all the fiber permutations, but what we can do, we are only concerned about those fibers that are related to the context. So context permutations are important for us. So from the context, we make a polyhedra, and for the polyhedron, there are these fibers are important. These permutations are important, and we open it like this, and we now what we will do from the space that from the base space, we will have a set of critical simplicities and virtual loops. And when you have this set, you will see which ones are valid. Some will go invalidated because it will not be, there will be, for example, no permutation from a if there is a for example a permutation ABA in this set, then it will be accordingly colored. Green means possible, red means critical, and blue means these consider virtual loops. But still, in the Hardy model, there is possibility of having global sections, some because it's logically contextual, or possible, or it's not strongly contextual. So you can have, like, for example, if you go for example, from A to A, for example, you can go from A to A, or like this, because we have to also consider A to 0 or 1. So it is 0 to 0. So you can go, and it's a loop, and it means there are families in this empirical model where there are which is possible. So it's not strongly contextual, it's logically contextual. And you can have, so this is just a theorem that we have the base space, the maximal base space, which is of genus 3. And the fiber space, we have this context polyhedron. And if you consider S4, it's a big group. It's a big group, and it can we have to see the subgroup of this S4 group, which we will see which kind of subgroup is which will, the things that you saw in the previous slide is in this group, and which is a subgroup of S4 symmetry group. And it's logically contextual because there exhibits some admissible global sections. And this is just another way of representation. I did not put the base space or the fiber space, but I just put it a flower way. It's a Cochen-Specker model. It's strongly contextual. If you go from any green, you cannot come back because there are already critical simplices and virtual loops that inhibit it from crossing this. And it's a very compactified picture. Yeah, these are because this is in the table there are this A, B, C. Yeah, and then you see which are possible, not. But yeah. No, it's I did not. I also three. Three A, B, C, like in the table. I think there are six, like 1, 2, 3, 4, 5, 6, 7. Yeah. Yeah. Then if you start from somewhere and you cannot, it's very. Actually, it has when we do the same construction, it appeared that the base space is of genus 6, and it could be represented by a different context polyhedra. It's in the next. So like this, in this there is a genus 6 doing the same construction, and then fiber space is like this, and it's strongly contextual. As you see, you cannot go in the previous slide, you cannot go around and form the loop, so it's strongly contextual. And and the other point is about the what are the additional structures that could be associated with the Turing machine in the current context to express these patterns. So it's about computational underpinnings of contextuality. So motivation is the idea of this computational epistemology comes from Feynman's lecture, which is very famous, in which he said, can quantum computation be simulated by Turing machine? And this question got answered, and it's now a field of quantum computation and information. But there was also, I can't say question, but there was a small, line or some small idea of Feynman that was inverse of this question, which is how does our conception of Turing machine constrain the physical reality? And he said it could be possible that we could have null categories of computation. And it's then in the same conference he met Patry, who is among the forefathers of computer science, and he said a vision of physical genesis of computation. He wrote a paper, and he said there should be some interplay between physics and computer science, so that we can have new computations, or we can. He's a pioneer of concurrency, you can say. And then there was another Wigner. He said non-locality arises from the incompleteness to observe all contexts simultaneously in interactive computation. And there is also Milner, who is a Turing recipient, and he said global context dependency in interactive computation could allow counterintuitive action at a distance, like non-locality and contextuality could arise if we allow these things to interact. If we keep mobile everything and you make them interact, there is a possibility that these things can emerge. And then there was also Abramsky, maybe. Who wrote a paper on fundamental structure of computation, and he said we don't know yet what are the fundamental structures of computation, and so many things have come, many things are back. Okay. So many modes of computation have, like Turing-like interactive models cannot reproduce the contextual behavior due to BilQC and Specker theorem, because it's a linear hidden variable thing. And contextuality is a topological property. That means we can see topological models of computation. And among the topological model, when we analyze, there is a static and fixed simplicial complex, and everything admits global order and constrained computation. In these models, computation is constrained, but the computation does not affect the global structure. So we think that computation does not depend only on the context, but also on their collective structure. So in this way, the computation we are trying to research is as a collaborative interaction between topological space and local manipulation rules. How does local, because if you see the sheaf theory, there is data on the vertices, and how they interact, and how this interaction is constrained by the topology of the space, and how topology in turn can be shifted due to these local rules. So, and we don't want to do this. Yeah, there are probabilistic versions, but even Turing machine can, if you have a bell-like scenario, you can simulate it on a Turing machine. In what sense? In a sense that you already have data. So when you already have data and then you make it run, you can simulate it. But in principle, these machines cannot express quantum contextuality or in these sense, because of BilQC and Specker theorem, which is like that, which means that anything that resembles a like local hidden variable means, for example, in Turing machine you have a tape, and you have 1, 2, 3, 4, and you have a computation function going from input to output, and it goes into the tape and it sees the value and goes like that. So this recalls a local hidden variable, like it's just a set, like, so it cannot reproduce this behavior. The reason why the machines cannot reproduce this, because they are not produced the What? There are. So we also proposed a model of computation, which is just a toy model. You can. So, but you don't have to go this. It's just a definition of a topological interactive machine, but we can go through example. Maybe you can. It's just some. So, for example, you have a simplicial complex K of 4 simplices, like V1, V2, V3, V4, like here, and 5 ones, 5. Okay, 5 1 simplices like edges, and you have also 2 simplices like this, and then. So we don't color code, we just randomly color code them. For example, there is a color coding of simplicial complex green or red, which is based on discrete modes theory, but in order to abstract the complexity, let's assign weights to each complex. So you have a weight on each simplex. It's 1 if it's generic simplicities. If it's 1, if it has a weight 1, then it's generic simplicity means it's green, and if it's 0, then it's red. It's critical, that's red. It's just a toy example to show you what's happening. So a simple illustration is like this. So we have this simplicial complex, and we have, so each vertex of K is a hyperspace. So this is because it has some data over it, which is represents a fiber, and we attach to each vertex Vi a projection map pi. So you have this pi I Si Vi. So you if you have so here pi is from Si to Vi, means you go down like this. So this is a one projection map. Yeah, 2 triangles. It's a very basic example. And on these triangles, we put some data. A? Which? Which one? I don't. Okay. We will. It's an action. It's an action. Like it. I will put some conditions when it will compute. So it's still. So we have 2 checks. First, we observe the weight of Ki for action. If we have to take an action, means if we have to compute from one state to another state in the fiber space between 2 states, state spaces, which is the first fiber space. And second check is we also put constraint on the number of states that it can hold, which is greater than n. So what it means, we have 2 checks. First is that the first is that if you have this and this is S1, this is S3, for example. So first check is to see that what is this has to see what is the color, what is the weight of this, is it red or green, for example, is it red or green. And second check is what is the cardinality of this space, how many states are there, is 3 or 4 or 5, whatever. So these 2 we have to say. It means computation between 2 state spaces is constrained by K. So it means a computation, I don't know why I'm so it means a computation from this to this is constrained by this, because if it's red, it cannot compute, it cannot make an action because it's red, for example. And if it's green, then it can make a function. And vice versa. And also we set this n, the state space. For example, we set 3. It means if there are 3 states, at least 3 states, it can compute. But if there is 2 states, it will freeze the simplicities to red. So this is the kind of interplay where the inverse map of pi of any state, this is a particular vertex. Okay, so it means if you have a pi, this map of Si, S1 is V1, for example. So it's just simple. The embedding, and we define an embedding, which is an inverse projection of pi corresponding to a particular S. That is means embedding of pi inverse of Si is the set of all Ki. It means it's a set that contains that S. For example, if this is S1, what is embedding? It's you just project it down and you see which are the sets in which this S1 is in this V1 is present. For example, V1 is in V1, V3, and V1, V2, for example. So this is the embedding of this example, for example. And then, so in this case, we have 4 fibers, and mod of S1 is 2, and that is S1 has 2 states, just like we already say, S1 and S2. Similarly, S2 is 3, and S3 is 1, and S4 is 1. Set a minimal bound to each S to be able to compute. Here we set a bound of this that is greater than 1. And here S3 is, and the mod of S3, S4 is 1, which means it cannot take part in computation by setting its corresponding simplices red. So these cannot take part because it's already, they have the mod, the max, they don't satisfy the condition that we put. So they are already critical. And then, so now we choose S1. First we check the mod of S1, which is 2. We satisfied our set bound that that mod of S should be greater than 1, something like that. So it's satisfying the bond. And then we see the pi inverse of S1, which is V1. And then we compute the embedding of V1, which is this. And then we check weight of Vi, which is 1. That is embedding intersection. The red is pi. There is no, it's not a critical. There is no, it's possible that it can. So when the second condition is also checked, it means Si can make transition to any of the state on S2. Say this function Ai, which is action, which is a function from S1 to S5. So it's making, so when all the conditions are checked, it changes from this to this. It makes a computation. So after the condition is, after the action here A15, then both conditions are rechecked. So in this way, what happens, the main thing is you are able to, it's a very toy model, you are able to compute, and the computation is constrained by the space, and the space is also changing because the fibers have now capability to turn it red based on the.
But I have a question. Is it like a automata or something over a base? Is that what you're trying?
Yeah, like that. Automata, but it has a space associated with it. So then these are checked. So it's just a pictorial way to say what I was saying. So we have a topological, we have this space and we have the state space. It's without this, it's a Turing machine. Like without this, it's a Turing machine. You go, yeah, yeah, exactly. So now when you put this thing inside it, different behaviors can emerge, like this non-contextual behavior, contextual behavior, or something like that. So it's actually the interaction of the local function in a topological global space. So this is the crux of these formalisms. How would a local function behave when it has to also consider the topological space into consideration?
Realized by a global. That's the statement that you want.
This
sort of computation cannot be realized by single.
Yeah, I want to be polite, like to say, but in principle, it cannot happen in principle.
No, you show that.
Yeah, we should, because as per Bell-Cotten-Specker theorem, Turing machines cannot, because there are two facets of when we say can a Turing machine express contextuality. There are two aspects of it. One is to say if you have data, and you can somehow use many Turing machines, for example, many concurrent Turing machines, and put probabilistic things on it, and you can make something happen. But in principle, it cannot. Like it's because it has already data. That's why it already knows what's happening in the system. But if it's in the kind of real time, kind of like it's coming, it will not observe this pattern. No. Yeah, only in quantum. Exactly. Yeah, now there are highlights, just highlights, like we did this, like a new framework. I did not discuss about this new framework because I thought it would be too much. So we just say generalization of sheaf theory, By the way, the interface loops, they are related to holonomy. You try to go around and you see if there is a flux, but I did not discuss it. So, and we, of course, this is not a good but it's just an approximation, but we are trying to refine it. And we applied this quantum model to these GSZ, PR boxes, Bell model, this, and this all. These are all models. So we applied the same formalism, and we expressed different strengths of contextuality. And we also said something about model of computation. And the slogan, the main theme is not of this work, but of the future work, is to say contextuality as a marker of essential structural change. So we think that contextuality is actually the marker of essential structural change. So if you know, for example, if you know where the change is happening, you don't have to count all the generic things. You just know where this change is happening, and you can construct whole of the space. For in our case, if you know, for example, the interface loops, where and how many they are and how many are critical simplices, you can through discrete Morse theory or other formulas, you can construct whole of the space. And so these are implications, but the main implication, the main thing that I'm interested in is to understand is first to check the complexity of this machine. For example, to say if this machine could be generalized, what would it be equivalent to Turing, or would it be in the middle, or would it be equivalent to quantum things? Quantum machine. So it's a check that we want to do. That is to say, what is the complexity of this machine, computational complexity, and we want to try it on some problem, for example, Jones polynomial. And we also are interested in understanding what are exactly the structures that are associated with quantum advantage, and that's it, I think.